everyone, welcome to SDC 2020 and to our presentation, Architecting Storage Application for the Public Cloud and Economy. I'm Orit Wasserman. I am OpenShift Container Storage Architect at Red Hat.
Hello, my name is Josh Salomon, and I'm an architect in the SES storage team in Red Hat. We are going to talk on the new software engineering aspects that the public cloud economy dictates, and specifically on storage applications related aspects. So let's begin. In this presentation, we'll explain three main items. We will start with explaining why we need storage applications on the cloud instead of using the cloud's native storage applications such as EBS and EFS. A second point we will explain is the public cloud structure and economy. This new economy is the thing that drives many of the changes that are required when moving from bare metal or private cloud deployments to public cloud deployments. And last but not least, the largest part of this presentation will be about tips and ideas how to develop storage applications that are public cloud friendly and efficient. These tips focus on storage, but can be used for other applications if you find them fit for your requirements. I want to start with an old story from the Windows 3.1 days, many years ago. The two pieces of code here represent two ways to write the Windows event loop in your application. Yes, in the old Windows days, you wrote it yourself, and it was not embedded in frameworks, which did not exist then. There are some differences in the code functionality, but for most cases, they were used interchangeably in literature, documentation, and real-world practice. And then something happened. Laptops started to become a commodity, and more installations of Windows ran on laptops. The difference between those two pieces of code is that the first one is battery manager friendly, and the second one is not. In other words, applications that used peak message wasted a lot more power and ran less efficiently on laptops. Why do I start with this story? Because it demonstrates how perfectly working applications became inefficient for some users because of some external, almost irrelevant change in the environment. This is exactly what happens when moving applications from bare metal or private clouds to public clouds. Applications that behave almost the same in traditional environments can show big differences in their operational costs when moved to public clouds because of the public cloud cost structure. And we can reduce the cost by changing the applications in ways that we did not think matter from a software engineering perspective when we deployed on traditional environments. So for public cloud deployments, we have at least one more dimension that we need to think of, the cluster ongoing cost, a dimension that almost does not exist when running on-prem, assuming you have enough hardware on-prem. So we start with one of the common questions that we hear all the time. Why do we need storage applications in the public cloud? Why not use the cloud's native offerings that is provided by the cloud providers, such as EBS, EFS, and S3, without working with additional vendors and products? There are several answers for this question, and here I want to outline some of them. First of all, resource optimization. Each cloud provider gives some sparse resource points in a multidimensional space. In the storage area, for example, Amazon gives EBS volumes with specific IOPS to size ratio. Today, 3 IOPS per gigabyte. So you can get a volume of 1 terabyte with 3K IOPS. You can get a volume of 2 terabytes with 6K IOPS, but you can't get 1 terabyte with 6K IOPS or 2 terabytes with 3K IOPS. This is for the GP2 storage, which represents per capacity only cost. There is an option to pay per capacity and per provisioned IOs, but this costs more. Naturally, you pay for what you get. So unless your needs fit exactly the EBS offering, you are paying too much. Since you pay for one dimension according to your needs, for example, 2 terabytes, and then you pay too much from the other dimension. You pay for 6K IOPS, but you may still work with 3K IOPS. So if we can combine several clients with different resource requirements, one needs more IOPS but less capacity, and the other more capacity but less IOPS, we can save on the usage of the cloud resources. Secondly, missing features. The cloud native offering does not necessarily have all the features that are required by each customer. For example, EBS is limited to a single availability zone. If you need to protect against availability zone failure, you need to add replication to your storage, which makes the deployment more complicated and more expensive. Another EBS limitation is volume size, which is limited to 16 terabytes. If you need larger volumes, you need to use a different storage system. And the third reason is the thin slicing. In cases where you need very small capacity, EBS volumes come with a minimal size, 500 gigabytes for HDD, for example. In other cases, you usually use small capacity, but may need more for burst in your load. In this case, you must allocate more capacity than you actually normally use. And when it's small capacity, you're actually multiplying the storage cost. Remember that scaling down capacity in EBS is not simple and requires migration to a new smaller volume. A flexible storage application can handle all these cases and reduce the required spare capacity by sharing it among many clients. So in general, if you are running a single application and you don't need some missing features, the cloud provider native storage may fit your needs. But if you run a cluster of applications and you want to manage the cost across a cluster, you may need to manage the cloud provider storage efficiently and use its resources efficiently to save costs over the entire cluster. So what is a public cloud? Note that I use here AWS terminology. Terminology may change a bit from provider to provider, but the concepts are the same. For convenience, we use AWS terminology along the presentation. We have several cloud providers, such as Amazon AWS, Microsoft Azure, Google, IBM, and others, all providing the ability to run your workload on their infrastructure. For the larger providers, we have regions, which are geographic areas in which the data centers reside. So if you need very fast access to your cluster on the cloud, you can choose to locate it relatively near to your location. Then we have availability zones, which are data centers located in the same region, in a reasonable distance from one to another, and fast communications within the region. So it can protect from physical or geographical disasters. Today in AWS, most regions have 3 availability zones. Some have more, up to 6 in Northern Virginia, but few have less than 3 AZs. For real protection from AZ failures, we need at least 3 AZs in order to prevent split brain. So a region with only 2 AZs can't provide full protection from AZ failure unless we have some observer from outside the region. It is important to note that communications between AZs in the same region is cheaper and faster than communications between regions. Hence, we want to deploy business continuity planes in the same region if possible. This is an old picture that explains the regions and the AZs in each region. It is not updated in terms of number. For example, North Virginia has 6 AZs today, but it depicts the architecture. Regions are not identical, nor AZs. It means that not all the resource types are available in all regions, and the prices may change between regions. Check your requirements and constraints carefully before you decide where to deploy your workload. So in order to understand why we need to change our thinking and our applications, we need to understand how the public cloud works. As the song says, money makes the world go round. So we need to follow the money and understand the public cloud economy and cost structure. The basic concept that the public cloud provides to the consumer is replacing CapEx with OpEx. Instead of buying the equipment and infrastructure, this is the CapEx, we then use them for a very cheap cost. Instead of this, we rent the equipment and infrastructure and pay only for what we use. This is the OpEx. This idea is very appealing to finance teams, but it has some caveats. If the cloud providers gain money from this business, does it mean that the customers lose money from this model? The answer is not simple, but I will try to simplify. If you run big enough, steady workload on the public cloud with naive resource usage and pricing schemes, you probably lose money relative to an efficient on-prem deployment. Note that the if part is complex here. For peak workloads, the public cloud shows great value for users. If you use more advanced pricing scheme, you can save a lot of money. And if you use your resources carefully, you can save even additional costs. Note that we can still have a win-win situation in which both the customers and the cloud providers make money, since the cloud providers reduce the cost significantly due to the huge size. So what do we pay for when we deploy an application on the public cloud? We pay for compute, either for the allocated resources, the nodes, whether they are utilized or not, or just for the execution. This is the serverless model. For the used storage, price is based on storage type, block, file, object, on media, SSD, HDD, on quality of service, and capacity. There are different price models, either per max capacity and bandwidth, or per capacity and consumed IOPS, or per capacity only but less reliability. This is the case for instance storage. For network bandwidth, either we pay for max bandwidth, whether we use it or not. This is the case for node bandwidth, or in some cases, we pay per network traffic, inter-AZ communications and external communications. For as-a-service applications, we can get from the public cloud many general purpose and infrastructure applications that we can use for a fee. For example, databases, dev tools, storage applications, AI and ML applications, and much more. And the bottom line is that efficient public cloud applications minimize resource usage even when the resources exist. This is in contrast to what we got used to in recent years, where many applications consume existing resources quite freely. As an anecdote, this was a very important practice many years ago when compute resources were the bottleneck of the available hardware. In the cloud, this may not be the bottleneck anymore, but it can save a lot of money to save on resource usage. So now we move to the main part of this presentation, how we can save on cloud operational costs. We will present several ideas related to the cloud resource usage as well as some application features that can make your applications and especially storage applications more public cloud friendly. So the first topic we want to consider for cost saving is the choice of the backing device. Naive approach for keeping storage in the public cloud would be to use a cloud-native storage. For AWS, it is EBS. This is the easy selection since EBS provides better reliability and it can be accessed by all instance types. And this was the first approach that we selected when we modified OpenShift container storage to work on the public cloud. But the simplicity and reliability come with a price in dollars. So we decided to consider using instance storage. The instance storage is equivalent to a storage that is directly attached to the service we use. This is the metaphor we get, but Amazon does not commit on the physical architecture of the hardware. From a user perspective, we get a fixed capacity that is paid for as part of the instance fees without additional cost for IOs or for use capacity. Let's see the differences between EBS and instance storage in more detail. Instance storage is cheaper, assuming you use the capacity. It is part of the cost of the instance, and you don't pay for additional capacity or IOPS. In EBS, you can pay for capacity plus max IOPS together, but then the capacity per IOPS ratio is fixed. This is GP2 model. Or for capacity and additional per provisioned IOs, IO1 and IO2 model, which costs more. Instance storage is also more performant. While GP2 is limited to 3 IOPS per gigabyte, and IO1 and IO2 tiers charge you for IOs, with instant storage, you can get very high throughput, up to 2 million IOPS and 30 IOPS per gigabyte. So is everything good with storage optimized instances? Not necessarily. If you want to get high performance, we can see that the network card of the instance becomes a bottleneck. So in the largest i3EN.24 extra large instance, the largest we have today, it gives us 60 terabytes of storage, 2 million IOPS, but only 100 gigabits per second networking. So it is a challenge, but also an opportunity if you plan accordingly. We will see more on this later. And now for the elephant in the room, reliability. Instant storage is less reliable than EBS in multiple ways. First of all, it is not replicated, unlike EBS, meaning that when the device fails, we lose the data. It is persistent across node reboots, but that's all. It is not persistent through instance stops, termination, or hardware failure. So we should be managing it carefully if we don't want to lose our data. On the other hand, all software-defined storage systems should know how to handle unreliable media and node failures. It is their bread and butter, and this should not be a reason not to consider instant storage. The last point I want to mention here is the reliability model of your system should reflect the media you are using. As an example, when using instant storage, your mean time to repair a node failure includes rebuilding all the data in the lost nodes to other devices. When working with disaggregated storage, such as EBS, your mean time to repair is usually the time it takes to disconnect from the volume and reconnect from another instance or pod. And last tip on device selection. In some cases, you may need to use EBS. As we saw, this is more expensive, so we recommend using it sparingly and consider some options that will reduce your cost. EBS already uses replicas internally to protect your data. It may be an overkill to replicate yourself as you do with unprotected devices. So you may consider using replica 2 instead of replica 3 in your application when using EBS. Obviously, it depends on your business requirements and the quality of service that you want to give to your users. But in many cases, reducing application replica count when using replicated storage such as EBS make a lot of sense. One other option is using erasure coding schemes instead of replica when possible. This hurts performance of the system, but can significantly reduce the cost while maintaining the data availability and reliability. When deploying on multiple AZs, you should add the cost of cross-AZ communication. Generally speaking, erasure coding fits better single AZ deployment than 3 AZ deployment. Last but not least in this area, when using EBS, you can use cheaper and even least reliable compute nodes. Since losing the compute node does not mean losing the data, and your MTTR is just spinning a new node and connects to EBS and does not rely on any data copy. And now I will pass the microphone to Orit.
Thank you, Josh. Next, I will continue and discuss more ways to reduce cost. Network is another resource software-defined storage uses extensively and can be costly. Communication in the same availability zone are relatively cheap, but cross-availability zone network is much more expensive and also has higher latency, resulting in slower performance. We would like to limit its usage, both to lower our cost and improve our performance. We have several techniques to minimize cross-availability zone communication. First, you can use a single availability zone, as not all applications need multi-zone reliability. For example, temporary applications, or applications that have a backup of the data when the data can be recalculated are suitable to run in a single availability zone. For example, cloud bursts. When you need more compute resources and you expand to the cloud to run a big temporary calculation. In this case, it doesn't make sense to use free availability zones. In the case of a zone failure, which is a relatively rare event, you still have your data in your private data center and can restart the calculation. Using single zone in this case reduces costs and shortens the runtime as you will have better performance. Zone read affinity, when you read the local data copy from the local storage daemon, reduces the cross-zone read communication and improve the performance. To keep protecting from availability zone failure, the data will still be available in each availability zone, meaning the writes will happen in free availability zones. Compression can reduce network traffic when the data is compressible. Sadly, not all data is compressible. It does require more computation, but today we have offload engines and can halt encryption strength in some cases. It should be used only when applicable. You should consider alternative topologies that can save on cross-AZ communication. Let's look at this example. If we want more reliability, we can use replica 4 instead of 3. With two availability zones, we'll have 2 copies of the data in each availability zone. Using a gateway for the communication between the zones will reduce the traffic. The data passes only once between zones on write. The primary in zone A communicates with the gateway, and the gateway forwards the data to 2 other storage daemons in zone B, saving 50% of the write traffic between the zones. The acknowledgement can go in the same way back to the gateway and then to the primary, or can go directly to the primary. As the messages are very small, the savings are negligible. You should always minimize the use of cross-availability zone communication. Next, let's talk about cloud elasticity. This cloud is known for its elasticity. You can get any resource on demand. As this is the case, there is no need to reserve capacity, as you can ask for more resources when the need arises. Always consume the smallest system size that fits your needs. An EC2 instance will cost the same if it's idle or busy. EBS volume costs the same if it's empty, full. If your instance is idle or you don't write to your storage, you still pay for it. This is a waste of money. Try to avoid it. As we want the smaller system, we need to use small building blocks to be able to scale with smaller granularity. If your compute unit and EBS volume sizes are units to scale with, large units will waste resources. For example, if you use EBS volume with 16 tera, you will need, each time you expand, the granularity will be 16 tera. So if you just need 4 tera, you wasted 12 tera. The same is for nodes with instant storage. If you use large nodes, again, your unit will be large. For example, if you use i3N for X large with 15 terabytes of data, again, the unit your unit is 15 tera. If your workload needs smaller capacity, you should use smaller units, like a smaller EBS volume with a half a tera size or 1 tera. The same goes for computation. You should optimize the size of your unit for your use case and your workload needs. Cloud provider has vast pricing model, tiers and options. You should study well your cloud provider pricing model. Use their free consulting services to understand it better and get more cost-effective architecture. If you can estimate in advance your capacity and your needs, you can find the most suitable pricing model, getting the best price for you. A saving plan is a pool of money you commit to the provider, like put it in a bank. It can be from 1 year to 3 years commitment. You can pay upfront fully or partially or not at all. It has a built-in discount. The longer term and the bigger upfront payment, the larger the discount. You can use it for any kind of resources you need, storage, compute, depending on your needs. You should choose the right pricing model that fits your workload and use case. Next, I will go more into details on the different pricing tiers for the compute instances. The on-demand instance is the most flexible one. You pay for usage by hour or second. When you no longer need it, you just terminate it and stop paying for it without any long-term commitment. You are not required to do any upfront payments. It's very flexible. You just decrease your number of compute instances on demand, but it's the most expensive one. You should leave those kinds of instances for unexpected surges of required capacity. The next tier is the reserve instance. It's an instance you reserve for 1 to 3 years. And again, you can provide upfront payments. Longer term means higher discount, bigger upfront payment, and another addition to the discount. Let's look at the M5 for X large. On demand, you pay 75 cents per hour. If you reserve it to 1 year upfront, you pay 45 cents, 41% discount. If you reserve it to 3 years, but without any upfront payment, you pay 33 cents per hour, 57% discount. If you reserve it for 3 years with fully upfront payment, you pay 29 cents, 62% discount. The prices, of course, change between different cloud regions depending on availability. You can use reserved instance most efficiently if you can plan your capacity in advance. You can also use them as a pool of resources for new workload and application as for the future. The last type of instance is spot instance. The cloud providers have a large spare capacity as they plan for the peak usage and need the hardware in place. Spot instance provide us with a way to get money for the spare capacity. The cloud provider let us use them very cheaply, but we take them back in case of a surge in the instance demand. In that case, you will get a 2-minute warning before the instance is taken away. The queues are maintained per instance type and availability zone. This means, for example, that your instance may be in high demand in one availability zone and will be evicted, but not in another. The same for a different instance type in the same availability zone. The cloud provider don't provide any information about the queue status or any tools to predict the chances of eviction of specific instance type. There are many companies that are using AI and machine learning to help with predicting to get longer notification. For example, Spot, an Israeli startup that was acquired recently by NetApp. The instances are very cheap. You can get up to 90% discount. Let's look again and then 5 for its cloud. On demand, it costs 75% per hour. But with spot instance, you can get it for 80 cents per hour, 56% discount. Those instances really are cheap, and other types can be even to get to 90% discount. How can we use spot instance? Stateless applications are perfect. All the system needs to do is launch a new instance in case of eviction. Near-stated applications, which are applications with really small states, can also be a good fit, as the small state can be persistent within the 2 minutes time frame. Another option is to use EBS to persist the application data. The EBS volume is not affected from an instant eviction, and the data will be available for a new instance. You do need to make sure the application can persist its data in the 2 minutes time frame and start running in a new instance with the EBS volume attached fast. You should make sure your application can move to a new instance quickly and can handle recovery in case the termination was not graceful. As the queues are per instance type, being able to run on a wide range of instance types will reduce the chance of all your instances being evicted in the same time. It's also increased the probability to get a replacement spot instance after eviction, as you have more options. As they are so cheap, we can have spare capacity without almost any extra cost. If you have more application instance running, the eviction severity lessens and you have more time to return to a steady state. This will give you more breadth to handle multiple evictions. In the worst case, you can always switch to on-demand instances which are guaranteed. This is a very good use case for them. In OpenShift Container Storage, we are working on spot instance support and also for OpenShift dedicated Red Hat OpenShift service. We are using all those methods to improve our reliability. Usually in the cloud, it's very easy to scale up, but downsizing is not as simple. The cloud provider support for it is lacking. For example, you cannot shrink EBS volume size, only enlarge it. The only way you can downsize your capacity is by deleting this volume, losing all the data on it. If you use smaller building block, in this case the EBS volume size, it will be easier, as you may need to recover the data in the volume. Smaller volume will have faster and easier recovery. The same goes for nodes with instance storage. If you use again a large capacity, downsizing a node will be much harder to handle. Downsizing is important for our customers as they pay for the cloud uses, in our case, in storage, for the capacity. If they can pay per storage capacity, they will be thankful. You learned today about the public cloud infrastructure and architecture. We discussed different architecture, tips and methods that can reduce your public cloud costs. Public cloud is all about elasticity and pay for what you use. Scale up or down, or on demand in every aspect, compute and storage. This is the key for a successful cloud implementation. You need to adapt your system and your application to be able to scale up and down dynamically, on demand. The cloud has a large variety of deployment options and pricing model. You should study the provider models and keep up to date with changes that can happen without much notice. Make your system flexible and adaptable to handle those changes easily. OpEx, OpEx, OpEx. Think OpEx. Keep tabs of a bill that can suddenly spike and can accumulate to a large sum. Make sure you optimize your cost in every aspect. Different resources like compute, storage, and network, and also the different pricing model. In OpenShift Container Storage, we are working all the time to reduce the cloud costs for our customers. Most of the tips we discussed today are already available in our product or are being worked on. We are always looking for additional ways to reduce the cost in the public cloud. Please take a moment to rate this session. Your feedback matters to us. Thank you. Feel free to send us an email for queries and questions and more information.